24 minutes. That's pretty good. Huh? I learned the top 1, top 5. I learned reasoning. I learned something new. I've already read the paper. Alex Net.
Good morning everyone, my name is Surya and today I'll be presenting something about barcodes, more importantly two-dimensional ones. Now all of us have seen barcodes in our lives, the standard barcode based on lines, there could be QR codes, and there are other variants in the market. But why do we even need barcode in the first place? The first barcodes came into existence back in the 1960s when the US government realized that because they were the pioneering, innovating country in railroads, people realized that they needed to track the different railroad components. There are different types of trains, different types of usages, so these are different specifications. So they needed to track the railroad components. So the first innovation was to put an actual etching, a manufacturing etching on the actual hardware of railroad tracks. Soon people realized that you can actually spread this concept into many other facets of life. The next step became grocery markets, putting it onto eggs, egg cartons and packets of milk, and back in the day with bottles of milk, so on and so forth. So of course, as technology progressed, things became much more sophisticated, but it all started with a one-dimensional barcode. This is in use even today, where you need to encode small amounts of data into, say, for example, in the supermarket, a pack of chips or a carton of eggs. You will see this type of a barcode etched on the backside of the product. So, how does this really work? We see black and white lines as a human being, but for a computer scan to recognize it, what happens was, this entire thing is broken into 95 different segments. And we understand as a human that sometimes it's black, sometimes it's white. But when you actually shine a computer scanner onto it, this is actually an infrared line, what happens is it recognizes a black as dark. It does not reflect any light, and therefore a computer recognizes it as a 1. A white line, on the other hand, does not reflects a lot of light because it's white. Therefore, the computer interprets it as a 0. This process is done for the entire sequence of the barcode. So once it's done, it starts classifying it into different bands. We have guard bands in the left, center, and right. These guard bands actually help the computer understand where the barcode starts and where it ends. It shouldn't recognize a barcode on the absolute left, absolute right, or even somewhere on top or the bottom as part of the actual barcode. After this, without going into the specifics of how the barcode works, it actually converts it into different numbers. These are ASCII represented. The beginning zeros mean something else. That's just verification mechanism to see that you're reading it in the right direction and not flipped around. And then you get the actual message that was meant to be encoded. This is how the world's first barcodes came to commercial usage. Of course, there was only about a limited amount of data you could pack into the standard one-dimensional barcode. If you went on and on, your infrared scanner wouldn't be as large. You can't afford to have an extremely large infrared code. So in the interest of packing more and more data into a limited amount of space, they came up with two-dimensional barcodes. This is known as the data matrix code, because this was the first 2D barcode that came into existence. Things became more and more sophisticated. We wanted error correction schemes, we wanted easy recognizability, we wanted damage control, so we came up with other forms. This is called a maxi code. This was patented by a German company, and this is what we know today as a QR code. This is a trademark thing, and all of us recognize it on site. We see it everywhere. On advertising agencies, Henry Ford used this to mark automobile parts. The caps of engine screws, the walls, everything in the Ford industry was used use QR codes to track the movement of certain parts, which components were in this engine, so on and so forth. So now when we recognize this on site, do we really know what goes on under the hood? What happens behind the scenes? How is this QR code generated? And more importantly, how is it recognized? Not just by a human, but by a computer. So if you look at this QR code, here is how it's actually broken down into different types of zones. Each zone has a very unique meaning to a computer when it recognizes these black and white dots. As we know, black would represent 1 and white would represent 0. So these are the different zones. The QR codes, as they evolve over time, technology innovators, they put version numbers onto it. The version can be denoted by the tiles in the blue zones. The format, you would want to style the pixels or the tiles. These are called, each black and white dot is termed as a tile. If you have a large sequence of black tiles or a large sequence or a cluster of white tiles, it's hard to distinguish the coordinates of each individual tile. So typically what's done is you put a mask over it, and the mask will ensure that there are no large clusters. For example, if you're given 3 black dots and everything else is known to be white dots, what is the coordinate of this? It's hard to determine. However, if you had a black, white, black, white, black, white, it's easier to determine this because you can count what differs between each and every row. So this is used to format the QR code. You apply a mask onto it. You have the data and error correction keys. The data is the grayed out zone. That has the information that you want to encode into the QR code, or data matrix code, short code, whichever. So because we wanted some error tolerance, we know today there are certain error detection codes, error correction codes. So some names that are buzzwords today are read Solomon codes and Hamming distance codes. So in the QR code standard, we use read Solomon error correction codes. That has a very high, it works on field theory, and it has a very high corrections ratio. The 3 trademark squares on the top left, top right, and bottom left are known as positioning tiles. These are meant to help a computer scanner or a camera, smartphone camera, to understand where the corners are. You don't actually need a large one on the bottom right. A smaller alignment tile is sufficient to really make sure you know where the actual dimensions are. And moreover, you have a timing zone. The timing zone is this region, the mandatory alternating black and white zone. The timing zone helps you understand, just like in this form, it's easier to understand the dimensions and the individual rows and columns of a QR code if you have mandatory alternating black and white sequence. So this helps you understand where each and every row is, thereby extrapolating a coordinate system for the QR code. So now when we look at the QR code, it makes a lot more sense. We understand how a computer algorithm would actually work under the hood. Now, this is a slightly larger QR code. Of course, even QR codes have their own dimension constraints. The solution was compounding. If we observe this, we see multiple of these alignment tiles that are kept everywhere in this larger, expanded, magnified QR code. This is known as compounding. Compounding helped maintain the standard and at the same time allow for a greater packing of data. These compounding features were seen in more other types of two-dimensional barcodes as well. The data matrix aligned it side by side along the solid edge and the dotted timing edge. So now that we're talking about how to create barcodes, what are the things that we need to look at when we're trying to design our own barcode? The first thing is known as Euclidean tessellation. Tessellation is the act of understanding how to tile an infinite plane using a regular shape. So usually architects would refer to this in the sense, how would you create a tiling pattern on your floor? We see outside our campus, we have a trapezoidal modification that looks like this. You can tile multiple of these side by side and create a tiling pattern using only this shape. But now, when you're coming to QR codes and two-dimensional barcode, we want a uniform, regular shape. So there is a proof that shows that there are only 3 potential candidates that can be used for regular Euclidean tessellation. So if we assume that there are consider that in this trivial example we use squares. At the vertex of where all these shapes meet, we assume this to be that same vertex. Assuming that we have n shapes that meet, meaning the side of the tile, that we are considering to have n sides, we know that this angle is 2 pi radians. So we know that, and if we consider this angle is alpha, n times n alpha is equal to 2 pi. This equation must be satisfied. The second thing we can observe is, we know that for any regular shape, and a regular shape is defined as a shape that has all dimensions of the sides equal and all angles of the sides of the shape is equal. So there we know that the internal angle is 180 degrees minus 360 divided by n, where n is the number of sides in the shape. So for example, if I took n as 3, this would become 120, this is 180 minus 120 is 60. An equilateral triangle has 3 sides and its angle is 60. So we know that we need to satisfy this. If we use these 2 equations, we will observe that n can only equal to 3, n can only equal to 4, n can only equal to 6. These are the only 3 values that satisfy. This implies that you can have a triangular tiling schematic and so on and so forth. You can have a square-based system, or you can have a hexagon-based system. A hexagon-based system would look like this, and so on and so forth. This effectively proves that we only have 3 candidates for a tessellating tile structure. The second component of our proof involves checking the area to perimeter ratio. So, as you know, we are in the business of trying to pack more and more data into smaller and smaller spaces. So that means that in a given a limited amount of space, if you limit your perimeter or if you limit your area, you want to pack more data into it. So essentially that means that for the given surface, you want to maximize the area of data that you pack into it. So the typical standard uses squares. So let's assume that it has a side of 8. We are trying to use hexagons now. So let's assume this to be of side S. If I mathematically show that, now if we assume the same perimeter, that means if 4a is equal to 6s, therefore I will get 4a squared is equal to 9s squared. Divide it by 2 and then square it, you will get this equation. We call it as equation number 1. Now we are trying to compare the areas. So we are trying to compare a squared versus root 3 by 4 s squared. This is what we are trying to compare. Once we simplify this, we will get an inequality saying that this area of the square is less than the area of the hexagon for equal amounts of perimeter. The implication of this is that once we start incorporating more and more sides, we have a better packing ability. And this is actually intuitive. We see this in nature as well. The circle, as we know, is the best form of packing. In a limited amount of perimeter, that's the maximum amount of area we can pack. And with the same justification, a circle has more number of sides, an infinite number of sides as compared to any other shape. So, but because we are limited to only triangles, squares, and hexagons, we are forced to use hexagons as our best candidate for maximum packing efficiency, for using a tessellated scheme. So now that we have agreed that hexagons are the ideal choice, we need to come up with a coordinate system. we know that our QR codes have a Cartesian coordinate system. We have an x-axis and we have a y-axis. Hexagons, we use a three-dimensional coordinate system. As you can see, these would be the coordinates, if you consider x, y, and z as the three axes, these would be the coordinates of neighboring tiles. You can extrapolate this to a larger schematic, and you will see that the coordinate systems actually follow. With every adjacent tile, two coordinates will change. So, using this, what if we proposed a coordinate system for a hexagon-based QR code? Something that would resemble this. What if this was our new form, the revamped version of the QR code? Something much more optimized, something much more concise, and just as efficient in packing data. So while this looks ideal, we need to figure out how it works. How do we pack information into this hexagonal-based QR code with the same number of features that the QR code boasts of? This is what I've broken it down into. We have a zone for data. This is where you would pack your information and your read, store, on error correction, modified data. We have a fringe that resembles the solid line of data matrix codes. We have a timing zone. We are manually alternating black and white tiles, which help detect the rows in the three axes of the hexagon. We have version information. We have masking information. And we have some error correction keys embedded here. The beauty of this is, with this we create a standard of how we can actually create a three-dimensional hexagonal structure that boasts of the same features, the advantageous features of data matrices and QR codes. So now this would be making much more sense now. We have the same features and it's a lot more optimized based on this structure. Now we come to the question of compounding. We see that QR codes have been compounded using more alignment tiles. We see data matrices have been compounded using alignment of the fringe zones and timing zones. And the fringe zones are important to denote the edges. The timing zones are important to denote the rows along each axis. Can we use the same concept in these hexagonal structures? If we consider this to be the one-dimensional alignment of these modified HexResponse codes or HR codes, this is how you would align them in 2 dimensions. You align them side by side such that the timing zone of one, the alternating black and white, aligns with the fringe of another. And also maintaining that the safe zone is merged. And the safe zone is important because it gives a guarantee that this is the boundary, this is the edge of the HexResponse code. There will be no information that is relevant to this HR code somewhere in these zones. It is fixed within these safe zone boundaries. This is how you compound it in 2 dimensions. The beauty of HR codes, which is an advantage that neither QR codes nor data matrix codes boast of, is that you can now compound it in more dimensions than 2. You can have a 3-dimensional compounding, and you can have a 4-dimensional compounding. This shows that using the same standard, you can now create visually attractive shapes, things that consumers would be aesthetically pleased to see HexResponse codes to be used as. With this schematic, you can now create patterns, you can create shapes using n number of dimensions that you so choose to use. You can compound it in any way using only the safe zone as the boundary. This is an advantage that QR codes and data matrix codes are not capable of distributing, yet the HexResponse codes now have this added facility. I have done a comparative study. It's primitive, but I encoded the phrase, this is a sample sentence, into a QR code, data matrix code, and HexResponse code. Visually, you can see that, and I made a constraint that the tile size, the perimeter of the tiles, has to be equal. We can see that the HexResponse code is actually looking a lot more concise than its counterpart neighbors. This is the work that I've been doing. Now, while it looks now somewhat algorithmic to generate this, how would we detect such an HR code? We've seen a detection schematic for a QR code. We've seen a detection schematic for the one-dimensional barcode. How would we detect this? This is also relatively straightforward. First, we detect the safe zone. This is important because we need to know where to look for the information. Where is the relevant information? Where is the irrelevant information? Then we detect the fringe zone. The fringe zone, along with the timing zone, will help indicate the orientation. So now if you have a guarantee that the fringe zone must be on the top right, top left, and left of the HR code, and you have a guarantee that the time zone, which is mandatorily alternating black and white, is on the right, and bottom left, you can now orient and rotate the entire HR code so that whenever you take a skewed picture, you can now align it into its correct orientation. After this, after you create the orientation of all the three axes, you detect the version zone and extract the version number that's used. This is a mandatory step because we need to know, based on the type of HR code you're using, other further detection schematics may change. So right now, because I'm still inventing it for the first time, it's still on version 1. Based on the version number, we extract all the other zones. In this case, that would be the mask zone and the error correction keys. Mask zone in blue, error correction in red. Once we have this information, we now have all the necessary tools to decode the data in the yellow zone, in the data zone that is already encoded using the Reed-Solomon error correction schematic. So after we detect the data zone, all the tiles in the data zone in a linear fashion, we now decode it using the keys from the mask zone and the error correction keys. After this, we store it in string, and the string is represented as the final message that is decoded from the HR code. This is how the detection of such a sample HR code would work. So in summary, we've seen that we have a higher packing efficiency using hexagons as compared to the only alternative triangles and squares. We've seen a simple generation schematic using the concept of multiple zones, safe zone, fringe zone, timing zone, etc. We've seen an easy detection algorithm which looks just as algorithmic as the QR code detection schematic. And we've also shown the capability of compounding in more than one dimension. So in effect, I am still in the process of inventing this, and I think this would be looking like the face of the new version of QR code that we'll be seeing in the near future. Hopefully I'll be able to complete a prototype. I already have a mini prototype that is used to generate the sample HR codes as well, but soon I'll be working on a detection schematic based on this algorithm. So if you have any questions, I'd love to answer them.
You said that n alpha has to be equal to 2 pi. Do both n and alpha have to be integral values?
Yes, n represents the
Number of sides.
Yes, and alpha is the angle. Of course, the angle does not have to be an integer,
Right.
but you need to find an alpha that corresponds to an integer n, and n cannot be fractional. It denotes the number of sides in the shape, the candidate shape.
So that means n wouldn't be limited to those three values of 3, 4, 6,
No.
right?
I can prove that n cannot be greater than 6. If we assume that, or we know that n alpha is equal to 2 pi, we know that alpha is equal to 2 pi by n. In terms of degrees, that is 360 by n. So when I take n as 6, this becomes 360 divided by 6, that becomes 60 degrees. And this represents a triangle. If we increase the number of n beyond this, we get an angle that's less than 60. And we know that we have no regular shape which has an angle of less than 60.
So you need it to be both the regular shape and
Yes, that is the requirement of Euclidean tessellation schematic.
what if n was equal to say 8, and in the same way you represent a hexagon with 6 different triangles, you represent
If I put
And
n
also
as
the-
equal to 6,
8.
5,
5, 8.
then I will get this is equal to 72. We have no regular shape that has an angle of 72.
Why not if you combine 5 triangles? You get regular pentagon.
Pentagon, that's the external angle. This refers to the internal angles. This is an internal angle.
Yeah, so the same way you're forming a hexagon with 6 different triangles, you can form a pentagon with 5, you can form one with 8, you can
They
form
won't
one
be
with 7.
regular.
Why won't they be regular?
Can you draw it?
Yeah, just draw a hexagon, draw a pentagon. Yeah.
So how would you draw this? This would be isosceles in nature, not equilateral.
Okay.
Because we know that this has to be 60 degrees for an equilateral triangle. But this is not evident.
And that's your criteria for the
Desiccation schematic. Any other questions?
In a barcode, the way they extract the zeros and ones is through the infrared.
Yes, it depends on the amount of light that's reflected.
Yeah. So what? I mean, have you worked on how you detect this, for example?
Yes.
Like I understood like your algorithms, like what each thing stands for, how you detect this, but how the initial future extraction of it, like how do you do that?
So in this schematic, the criteria for judging the endpoints of the barcode would be the guard band. Guard bands are denoted by a sequence of 101. If you see no other 101 to the right of it, then you know that this is the right guard. If you see no other 101 to the left of it, you know this is the left guard. And then you can estimate where you would want to find a center guard. If you find a center guard, you're sure that these are the boundaries.
You know, I'm saying like this is after you've got the 101, right?
Yes.
And you get the 101 from the infrared light.
Yes.
I'm saying that step in your hexagonal QR code.
How it will work when you have this one?
What sensor are you using? Yeah, what sensor are you using?
Here we use computer vision technique, just like how we use our smartphone camera to detect QR code. QR code we don't use an infrared light to detect the individual tiles. In QR codes what we do is we extrapolate the timing zones. And the timing zones are used to further in later steps the coordinates, the x and y coordinates of any individual tile. So now you know the dimensions of this. You've extrapolated this. You know this. So now you can judge where the individual rows are going to be. Likewise, in theory, you can extrapolate where the individual columns are going to be based on this timing zone. So now with these two timing zones, you can now find the coordinates of any given tile using these as the axis. Likewise, in HexResponse code, using this, and this as the primary axis, the three-dimensional hexagon, you can now extrapolate the coordinates of any given tile using a lining from this, and likewise a lining from this. That will be represented as this. Sorry. Using this coordinate system. So this coordinate system can be extrapolated using the timing zones of the HR code. So once you have those timing zones, you won't need infrared anymore. It will work on the same schematic as your Gaussian data metric system.
How is the grid working?
So we know that, let's assume that this is our origin. It has an x, y, and z coordinates. So now I will try and justify this alone. Now we see that the z-axis is actually not coming from the side, it's coming from the corner. Likewise, the x-axis is coming from a corner and the y-axis is coming from a corner. So if I draw a straight line, this would represent the y equal to 0 plane. Likewise, if I draw a straight line like this represents the z equal to 0, and this represents x equal to 0. So with respect to this plane, is this moving left or right? No, it isn't. It's just coming, if you are standing here and looking down, just by moving here, are you changing your x coordinate? You're not. You're not moving left or right. Therefore, the x remains 0. If you look at the z plane, are you moving left or right? Yes, you are. By coming down, in the perspective of this angle, you are moving. So your z coordinate will change. Likewise, in a y-axis, you're coming to the right. In the act of moving from here to here, you are moving right with respect to this plane. Therefore, this will change.